Hello, this is the second part of the lecture on the Bose gas. So let me remind that last time we discussed that this formula, the relation between the pressure and the internal energy for the gas of photons. And next topic will be uh, the simple theory created by Einstein, who tried to explain the Planck distribution based on some physical arguments. And this is what's called his theory of A and B coefficients. And the basic idea of his theory, the main ingredient, that there is a statistical attraction between free bosons even when they are not interacting. Okay, and we've seen it already before when we calculated corrections to the pressure, to the classical pressure of the ideal gas for bosons, and then the pressure was less. The first of the correction was less. And for fermions, because they repulse, it was great plus correction, and for bosons it was negative sign. So there is a statistical attraction, and so the pressure is less. And okay, so what is Einstein's theory of A and B coefficients? Consider a two-level atom in the wall of a black body cavity. And for simplicity, we assume that it has two energy levels, E1 and E2, such that the distance between two levels is equal to the Planck constant times the frequency. Okay, and the population of these two levels in equilibrium is maintained by emission of an absorption of photons of the frequency omega in the black body radiation. Okay, what it means that we have two levels, and when, for example, is a photon emitted, when the electron moves from the level 2 to the level 1, it emits a photon of frequency h omega. By the way, yeah, it should be in here, not h bar by h. Okay, it depends on the definition, okay? But I guess it should be just h, not h bar, because omega is 2 pi nu, okay? So there are these photons emitted by the atom, but there are also photons in the cavity, okay? And Bose enhancement means that the rate of emission and absorption of photons by the atom is changed by the presence of the photons of the same frequency in the cavity. Okay, so there are three possible scenarios. Let's assume that N1 and N2 denote the number of atoms in level 1 and level 2. Einstein postulated the following equation, the following rate equations with where U is the spectral density or energy density of photons in the cavity. Okay, so what it means then, when the atom is emitting a photon and moving from the level 2 to the level 1, which is called spontaneous emission. So the number of atoms in the state 2 changes proportionally to the number, to this N2 with minus coefficient, because the photon is emitted. So with some rate minus A, and obviously the speed of this change should be proportional to the number of atoms in state. Similarly, if this if the number of atoms in the state 2 decreases, then the number of states in the state 1 increases by the same amount. So the total number of atoms doesn't change. Not total number of atoms in these two states doesn't change. And so this is given by the same quantity with plus. Now there is stimulated emission, which says that there is a gas of photons of the same frequency in the cavity. Okay, and this gas of photons actually kind of attract the photon emitted, and they stimulate an extra emission. So because of this gas, they kind of trying to attract this photon and encourage the atom in the state 2 to emit the photon of the same frequency. And so this stimulated emission, again, number of photons of atoms in the state 2 decreases. So with some coefficient b, it should be proportional to the number of atoms, but it's also proportional to the density frequency of atoms in the cavity. And this is also quite a reasonable assumption. So when there is density of photons in the cavity is 0, there is no stimulated emission. Okay, so once it starts increasing the density of photons, there is a stimulated emission proportional to the density. And again, the number of atoms in the state 1 increases by the same amount. And finally, photon absorption. So when the atom in the state E1, it can absorb the photon of the frequency omega or nu and move to the state 2. And then the number of atoms in the state 1 will decrease by this quantity, and again it will be proportional to the density of photons in the cavity, because if U is 0, no photons, so nothing to absorb. And correspondingly, the number of atoms in the state 2 will increase by the same amount. So these three processes, first and third, are very natural from the point of view, physical point of view, but the second one, stimulated emission, is due to statistical attraction of bosons. So bosons in the cavity want to create more bosons because they are more photons, because they attract the photons and stimulate emission to atoms to move from the level E2 to the level E1. Combining these three laws, we can calculate a total rate change or a total rate change of atoms in the total rate change of atoms in the state 2 and the state 1. And this is just summing up all previous contributions, where U here is the energy density of photons per unit frequency in the cavity. Once we reach equilibrium, we must have that these derivatives should be equal to 0. And this imposes this constraint between N1 and N2. Now, in the equilibrium, we expect that we should expect the Boltzmann distribution of the densities, and it determines a relative population of levels. We remember that if we write Boltzmann distribution for N1 and N2 and divide them, then take into account level degeneracies, then the ratio of N2 to N1 in equilibrium should be the ratio of degeneracies times the relative Boltzmann factor. And the relative Boltzmann factor is basically the distance between two levels. Okay, so for the we need to take exponential of minus beta E2 plus exponential of beta E1, and because E2 is equal to E1 plus IH omega, we get this equation. Okay. Now, one can show that these rates, beta and b prime, they are proportional, their ratio is proportional to the ratio of degeneracy. We won't look into this case, but we assume for simplicity that degeneracy levels of both states are the same, G2 equal to G1. Okay? Then one can show that the two coefficients b and b prime should be the same. So we consider this case for simplicity. Now we can take this equation, and if b equal to b prime, solve it, for example, as respect to the spectral density u, and we result in this formula, okay, which is nothing else as a Planck formula eventually for the density states in this photon gas. And let's notice that if we drop the stimulated emission term, which is corresponds to b equal to 0 in this relation, then again expressing out of here u as a function of n1 and 2, and using this Boltzmann law distribution, we immediately see that we obtain the high temperature Boltzmann distribution. Okay, so this is somehow, you can look at it as a physical explanation, this theory of A and B coefficients as a physical explanation that in the presence of photons in the cavity, there is this statistical attraction between photons, and as a result, the spectral density is described by this law, which is nothing else as a Planck law. Okay. And the next topic we are going to look at is bosons in solids, okay, which are called phonons. So let me remind you how we calculated the specific heat of solids at high temperatures. One of the basic models to describe a solid crystal at high temperatures was the Einstein model. In the Einstein model, each atom is treated as an independent 3D harmonic oscillator. And this model correctly describes thermodynamic properties at high temperatures, when we can assume that all atoms vibrate independently of each other. At low temperatures, the situation is different. Thermal fluctuations are not very high, and if you wiggle one atom, its neighbors also start to wiggle in a complicated way. At low frequencies, large group of atoms can move together, and at high frequencies, atoms are moving opposite to its neighbors, in opposite directions. These small amplitude vibrations can be described in terms of normal modes, which are harmonic oscillators. And the quanta of these normal modes are called phonons. Phonons are not real particles. They are quasi-particles which describe collective degrees of freedom in solids at low temperatures. They obey Bose statistics, and their number is not conserved, so their chemical potential is zero as well as for photons. You can actually do a simple mathematical model simulating these phonons. For example, if you take a number of harmonic oscillators coupled together, and if you excite them, and if you move to the Fourier space, make a Fourier transform, you see that all these harmonic oscillators will move all together in a complicated way because of the interactions. But in the Fourier space, in the frequency space, you will see that these modes are localized. And this is a mathematical model of phonons. You can look at this. Okay, so it's not very hard to do. So basically phonons, they describe, as I said, collective degrees of freedoms at low temperatures. Once temperature starts to increase, there are thermal fluctuations, and these thermal fluctuations completely destroy these collective degrees of freedoms, and atoms start vibrating independently, as in the Einstein solid. Now, the phonon energy and momentum are related in exactly the same way as for photons, but the difference is that Cs is the propagation velocity of phonons, and it's not the speed of light. The phonons, of course, they are moving with much lower speed, and we can relate it again to the frequency of oscillations. With photons, we had only two possible polarizations, two modes for each photons. With phonons, there are three modes of oscillations. One mode is longitudinal, corresponding to sound waves, and two transverse modes. What it means, it was shown on the first page of the slide. So if I move back, so this is exactly this picture shows. Here is a longitudinal mode for phonons. Basically, the lattice, it just deforms in the horizontal direction. Okay, so that way, so this here atoms closer to each other. Here they just further away from each other, and so there is a propagation in the horizontal direction. Those two transverse modes, then when the atoms, there is a wave, but at atoms they vibrate in the transverse direction, and there are two such directions, so there are two transverse modes and one longitudinal mode. Okay, so the difference between a phonon and a photon is that frequency spectrum of a phonon has an upper cutoff. Remember that phonons can have all frequencies, and this was the reason in the classical physics for an ultraviolet catastrophe. But imagine that your phonons, they sit in your system, your solid, in the box of the length L. And so phonons, first of all, they're low modes, they are restricted to the size of the box, so the half wavelength length is equal to the half of the box. But when you excite more phonons with higher frequency, their length the wavelength decreases, and etc., until we reach the size of the spacing of the lattice. Okay, so there is the minimum value for the length waves of phonons, and as a result, there is a top frequency, a frequency cutoff, because there is a lambda minimum, and frequency is inverse proportional to the length, wavelength. So as a result, there is a frequency cutoff from the top, from above, and this resolves this ultraviolet catastrophe for phonons. Okay, so this is all done by Debye, who proposed this model in 1912, and this is why it's called a Debye model of solids. So consider waves in a box of volume V with periodic boundary conditions, and we label modes by wave vector k. We already calculated the number of modes in the elementary volume in the wave vector space T3k to be this. We've done it again at least a couple of times. So we can introduce the frequency distribution function for a particular angular frequency omega, that the numbers of modes in this interval should be equal to the number of modes. So again, we are looking at the spherical shell in the three-dimensional momentum space. This is the area of the shell, 4 pi k squared. This is the thickness of the shell, so that's the volume of the shell, and this is the number of modes in this per unit volume in the shell, is shown by this formula. Okay, as a result, this is roughly speaking the number of modes sitting at the frequency omega in the interval d omega, and this is a simple change of variables from k to omega given by this relation between the angular frequency and the wave number. And the factor 3 here corresponds to the 3 phonon modes. And from now on, I will not use the notation CS. I will simply leave here the speed c, assuming this is not the speed of light. It's the speed of phonons in the lattice. Okay, so we get the following frequency distribution for phonons in the lattice. The total number of modes of the system is 3n, because there are n atoms, and so each atom has three possible degrees of freedom. Okay, as a result, we can define the so-called cutoff dBi frequency, omega m, by this requirement that if we integrate the density of phonons per unit interval omega from 0 to this cutoff frequency, and this cutoff frequency, let me remind, it's due to the minimal spacing of atoms in the lattice, then we should have it should be equal to the total number of modes. And from here, when we calculate this integral, f is proportional to omega squared. So the integral of 3 omega squared is omega cubed. And so we will get omega cubed of this dBi frequency. And as a result, we can calculate it in the following form as a function of the density of atoms in the lattice. Okay, so with this frequency, the characteristic cutoff energy h omega m, it also defines the so-called dBi temperature. Okay, this is just a formal definition. This is a characteristic energy of the cutoff, and we define the dBi temperature from this relation. Now, so in the dBi model, a solid at low temperatures is represented by a collection of phonons. Thermal fluctuations, they are negligible, so atoms move collectively, and this collective behavior can be described by phonons. At higher temperatures, phonons become interact, or their picture for this collective degrees of freedoms, is destroyed by thermal fluctuation, so this picture becomes not very accurate. So here's a typical frequency spectrum for solid line for aluminum, and the dashed line shows this dBi distribution function. Okay, so you see that at least there is some agreement up to some. At low temperatures, it's indeed quadratic, and there is a clear peak, and that dBi frequency, and then there is this fast drop here. So this is somehow described, has a reasonable agreement. Of course, there are these peaks and drops due to intermolecular forces for a particular material. So the density the function f of omega, its correspondence is not very good because of these deviations. But once you integrate it over all frequencies, so roughly speaking, this top part will be compensated by the above the curve will be compensated by the parts below the curve, and the integrated expression has a very good accuracy. Okay, this is what I am going to demonstrate in 5 minutes. So, who was Mr. Debye? Debye was a Dutch-American physicist and physical chemist, and he won a Nobel Prize in chemistry. So he was enrolled in the Aachen University of Technology, not very known, and he first completed his first degree in electrical engineering, and he studied physics under the theoretical. His supervisor was Arnold Sommerfeld, who later claimed that his most important discovery in his life was Peter Debye. So his first major scientific contribution was the application of the concept of dipole moment to the charge distribution in asymmetric molecules. And as a consequence, the units of molecule dipole moments now called Debyes in his honor. So in 1912, he extended the Albert Einstein theory of specific heat to low temperatures by including contributions from low frequency phonons, what is called now Debye model. He also worked on the Niels Bohr theory of atomic structure, calculated the effect of temperature of X-ray diffraction patterns of crystalline solids with Peter Scherer, and for these achievements he received a Nobel Prize in 1936. In 1940, he moved to Cornell University in USA, when he stayed for the rest of his life. Okay, Debye was somehow the opposite. He was not a friend of Einstein. He was one of his numerous enemies. And in fact, Einstein in the 1940, he wrote to the Cornell University administration specifically asking not to take Debye for a position there. One of his arguments that in late 30s, Debye collaborated with Nazis in Germany. Okay, and later on, there is a Debye Institute of Theoretical Physics, and later on, there was some evidence published that around late 90s, I believe, that, or even earlier 2000, that on Debye collaboration with Nazis, and after this, the institute was Debye Institute was renamed. Okay, so basically his name was removed from the title of the institute. But later on, there was a special commission in the Cornell University which investigated this matter, and they came to conclusions that there was no certain evidence, basically any evidence, solid evidence on Debye collaboration with Nazis. As a result, his name was just that returned to this institute, and there is still now Debye Institute of Theoretical Physics. Okay. Now, so in the Debye model, we can also calculate the internal energy per atom. And we do it exactly as in the same way, using the Planck distribution. And this is the energy per atom. And we sum over all energy levels with Planck distribution, with the Planck computation numbers per particular energy level. And then we transform it to the integral. But now this integral runs, as I explained before, not over all frequency range, but from 0 up to some top frequency or top wave number. And this is the expression. And if we make a change of variables from the wave numbers to frequencies, then we get the following expression, for internal energy per particle in solids, where the top frequency is the dBi frequency. And here is exactly the Planck distribution. So this formula looks very similar to what we had for the gas of phonons, except that the integral now, the top limit is now finite. Again, doing exactly the same trick, we can change variables in this integral. And if we introduce, because the integral now is finite, that frequency omega will enter the final result. Okay. And if we use the variable, I before defined dBi temperature as being kT dBi temperature equal H times omega. And if we introduce this variable, effective variable dBi temperature over the temperature, then the internal energy per particle, it becomes, after the change of variables, 3 kT, a function d of u, which is called the dBi function. And this form of this dBi function is given by, after you change variables, it's given by this formula. So it's again a simple change of variable. I believe there is a missing factor here. So this should be somewhere, it's k cube. So k is proportional to omega, so there should be k cube here. Okay? So there is, once once we change the integration, should be some h omega cube here. Okay, there is a typo here, so it should be proportional to the omega cube. And once we do the change of variables, there will be t cube in here. So this formula is correct, and you need now to change to the frequency, and there will be an extra factor here proportional to omega cube. So this is internal energy per particle for any temperature. U is basically the inverse temperature, and here is d of u is this dBi function. And once we have this expression, we can actually do the high and low temperature expansion for this dBi function. So when temperature is high, u is very close to 1, and you can approximate this integral easily by expanding it, and dBi function it basically becomes 1. And in this case, the energy per particle is proportional to 3 kT. Now, when temperature is very low, u is very large, and dBi function has the expansion 1 over u cube. Okay, and because u is the inverse temperature, so it becomes dBi function behaves itself like t cube, a cube of them. And the specific heat in the dBi model is obtained by differentiating this expression with respect to temperature. When you differentiate this expression with respect to temperature, you first differentiate this t, which gives you, and divide by nk. This will give you 3 du, but because u also depends on temperature in terms of this variable u, so as a result, you need to differentiate du, and you get this expression, second term. And this is supposed to be the universal function of u. There are no any parameters here, because d of u is given by this formula, and it depends only on the single variable u, and where a single variable of u is given in terms of the dBi temperature. So once you know the dBi temperature for any solid, the specific heat for the solid in all temperature intervals should be given by this formula. A universal behavior for different materials. And this has a great confirmation a great agreement with experiments. So if you look at different solids like aluminium and others, then if you define, you can calculate dBi temperature for any particular material. And if you plot the specific heat versus temperature over dBi temperature as a variable of this universal variable u, okay, then all materials, basically they have the same display, the same curve. Okay. So at very low temperatures, the specific heat behaves like T cube, which is a reflection of the linear dispersion relation. And at high temperatures, it approaches 3 nk, okay, in agreement with the law of Dulong and Petit. And this 3 nk, it corresponds to the equipartition of energy among 3 n-harmonic oscillators, because you represent each atom as a harmonic oscillator. Each has the energy p squared plus q squared, 2 quadratic degrees of freedom, kt over 2 per each degree of freedom, so the total energy is total specific heat for each harmonic oscillator is kt, so it approaches 3 kt. Okay. And by the way, I didn't mention it here. When I calculated the internal energy, there was the factor 3 here. Originally, we had the factor 2 in front, but because the 2 was because of the photons, they have 2 possible polarizations. So we replaced, we put a factor 2 because there were 2 possible polarizations of photons. Now, phonons, they have 3 possible polarizations, 2 transverse and 1 longitudinal. And this is why we replace here the factor 2 with the factor. Okay. And the last slide is related to the electronic specific heat, which we already calculated in the limit of high temperature. And so let's try to understand it better using this Debye model. So we see that at room temperatures, T, so basically Debye temperatures, they are of the order of the room temperature, maybe 100 degrees plus minus. And so at high temperatures, when temperature is of the order of the Debye temperature, the specific heat is approximately 3 mK. Okay, so there is per particle, there is a contribution to the Debye specific heat coming from electrons of the order 3K. But the electronic specific heat in this region at room temperature is of the order T over T Fermi K. And because electrons, they are fermions, okay? So there is an electronic specific heat which we calculated before, and temperature of Fermi is equal to approximately up to 50,000 degrees. It depends on the material, and so this is a very small number. Okay, but Debye specific heat, it comes from specific heat of phonons. So at low temperatures, electronic contributions, they become more important. And as a result, we can expand the specific heat up to the third order in T. So this is the leading order of the electronic specific heat. And there will be higher corrections to that, like quadratic term, cubic term, and so on. And then at cubic term, Debye contribution of the specific to the specific heat comes into play. Okay, so typically temperature of Fermions, as I said, around 40,000 kelvins, and Debye temperature about 300. So if you look at the order of coefficients in this expansion, that the first coefficient is of the order C1, T minus 4, then the next one T minus 1, the next one T minus 13, and the last one is 10 to minus 7, Debye contribution. So we can safely neglect these two terms and consider this and these contributions from the first order of the electronic specific heat and then contribution from phonons. So we should expect that for all ranges of temperature, the behavior is to be expected as AT plus BTQ. Okay, so at very low temperatures, this quantity dominates because T is small, but at higher temperatures of the order of the room temperature, as we've seen before, that a contribution to the debye from the debye contribution starts to dominate. And this is so this formula should describe the specific heat for electronic specific heat in all ranges of time. And this is indeed is very good, can be confirmed experimentally, and there is a good agreement of this formula with specific heat of electrons for all ranges of time. Okay, so this is the end of my lecture on the Fermi, on the Bose gas, and David will take over next.